Hello, my name is Alex. I'm a member of product team, and today we will talk about anomaly detection again. We had a brilliant talk from Wolfgang, who did a great job, did a great research on anomaly detection, and his idea to feed multiple streams of data to neural networks is really impressive. But this approach requires some knowledge of your data. So if you know your data, if you know how your item values correlate one with another, if you know how to train, if you know pieces of your data without any anomalies in advance, so you can train them, this will work really well. But we, from core product features standpoint, also must think about more generic ways to do anomaly detection. So let's start with a quick story. So a while ago, management came to our team with a request. So we need to get some AI features, and well, we asked what features, whatever will work, something useful and very AI. So I naturally did what anyone would do. I went to ChatGPT and asked this question. And here is the first idea that ChatGPT came with. Anomaly detection, it's a perfect use case for AI. Now, ChatGPT didn't place anomaly detection at the top for no reason. It's basically wisdom of the internet, wrap it up in model, so we can be pretty sure it's one of the most talked about topics in monitoring. And a lot of people think that this new shiny tool will solve all their problems, and we will try to find if this is the case. So what is anomaly? We all have intuitive understanding of what is anomaly in everyday life, but our everyday understanding doesn't always match some technical realities. So to make sure we're on the same page, let's start with a clear definition. So Merriam-Webster defines anomaly as something different, abnormal, or not easily classified. But since we are dealing with time series data, we need to be more specific about what anomaly means in our domain. So we define an anomaly in a time series as a rare or unexpected point or sequence occurring over specified time interval, considered unusual or undesirable. This definition is simple, but it also helps us to understand what isn't considered an anomaly. For example, traffic to an online shop, which will spike before Christmas, is expected. So even though you see some spike, it's not an anomaly. Similarly, if you have some faulty temperature sensor, for example, that constantly gives you, and usually low values, that's not an anomaly either, because these values aren't rare. So there is no shortage of definitions and classifications of various anomaly types, but well, some divide anomalies into 2 types, some to 3, some even up to 8. But to keep things simple, let's focus on 2 main types. This is a point-based anomaly and subsequence-based anomalies. Point-based anomalies are simple and well, obvious in many cases, especially when there is no seasonality involved. These types of anomalies are typically short in duration, making them very easy to spot. And detecting point-based anomalies is often straightforward with some statistical methods. For instance, using Zabbix function like std-def-semp, this function can help identify data points that deviate significantly from the mean. Now, if you look at this distribution histogram on the right, it shows outliers, which are typically far from average values, and usually everything which is 3 standard deviations far from the mean is anomaly for sure, for point-based anomalies. Subsequence-based anomalies. Subsequence is a continuous portion of time series. We can think about it as a small window of our overall time series. Subsequence-based anomalies occur when a specific part of time series doesn't follow usual pattern. It is not about just one data point in this case, but rather about entire subsequence acting differently, like in this example. In this graph, orange section shows this kind of anomaly. The whole subsequence behaves strangely, and for these kinds of anomalies, we are not looking for one or more single outliers like spikes or drops, but instead trying to spot strange patterns over time. So, what are the characteristics? Subsequent-based anomalies typically longer duration. Such anomalies last longer since they affect multiple data points. They are harder to spot visually. Since they cover longer periods that tend to blend in with surrounding data, so they are trickier to notice at glance. They require more complex detection, and here you just cannot typically rely on simple formulas or standard statistical methods. And this distribution histogram shows the difference between point-based anomalies and subsequence-based anomalies. In this case, anomaly data blends into mean values, so it's pretty difficult to distinguish normal values from such subsequence-based values, which we consider anomalous. So, how about Zabbix? Zabbix has some trigger functions which are relatively good at detecting spot anomalies. These are standard deviation, MAD, it is a variance function, and it is baseline functions. Then there is a trend STL, which has been already covered a little in Wolfgang's talk. TrendSTL is more advanced and it can handle seasonality, making our most powerful anomaly detection function. But let's see what is its features. It implements STL, well-known STL anomaly detection algorithm. It breaks down data into three components: trend, seasonality, and residuals. And by analyzing residuals, we can find which points are outliers. But we need to keep in mind that STL works best on data which has some seasonality pattern. If your data doesn't have seasonality, you may not get good results with this function. It has its shortcomings. First, it requires up to 7 parameters to set up. Sometimes it even may feel like you need some special education to configure this function. Second, as I mentioned, since it works with a season, you need to be careful to choose its seasonality. If you haven't chosen seasonality properly, it will not work as expected. Another limitation is that even though it supports seasonality, it doesn't support multiple seasons. So, for example, if you have both daily and weekly patterns, you may end up with residuals that should be actually attributed to some season component. And finally, subsequence-based anomalies cannot be detected well by TrendSTL. So it's pretty obvious that Zabbix could really benefit from more anomaly detection tools. But the question is, what exactly do we need and what are our priorities? Naturally, there is no one-size-fits-all solution, and every method has its trade-offs. So let's set some key requirements. First, probably, is the performance and efficiency. We need low CPU and memory usage because we will probably be processing this anomaly detection not for one item, but for many items at once in bulk. So, and for the very same reason, we need real-time or near real-time results to use these methods and triggers. Ease of use. Of course, so the less knobs and switches is better. TrendSTL is sort of difficult to understand what every parameter is about. Then we need to easy understand, and it should be easy to interpret results which are coming from such anomaly detection methods. So we can trust these results and we can explain these results to others. The next one is subsequent-based anomalies. As we found earlier, subsequent-based anomalies are pretty tricky to detect, but we would like to catch them as well. And multiple seasonalities, yeah, it would be also good because TrendSTL doesn't work with multiple seasonalities. Now, let's look at the methods available. There is definitely no shortage of anomaly detection methods, and some simple, others more complex. What you see here is just some of them. Next, let's see if any of the methods can meet our requirements, but first let's quickly look at how we classify them. So, it has been already mentioned today that time series can be multivariate and univariate. And there are two algorithm classes that works with this data. There are multivariate algorithms and univariate, and from Zabbix core features standpoint, we need to focus on univariate time series to provide better basic anomaly detection tool. So it's important to master straightforward scenarios before multing to multivariate series. So in this talk, we focus only on univariate ones. Training types. Anomaly detection methods also differ by training types, and there are supervised training, which requires manual data labeling. There is semi-supervised training, which doesn't require some labeled data, but it still requires some clean data stream without anomalies to be successful at further anomaly detections. And finally, there is unsupervised method, which requires no training. It's probably fair to say that for real-time monitoring, supervised and semi-supervised approaches are very difficult to implement in practice. Even so, maybe it is possible for some scenarios. Now, there is a wide range of research being done on anomaly detection methods, from deep learning techniques to more traditional approaches. A lot of them. So just last week, I did a quick search, and just last week I counted 39 new articles on this very topic. This highlights just how diverse this field is and how many different strategies available to deal with the problem. Let's look at different types of detection methods we can use. So there are statistical methods. Simplest one, it is Z-score, when you just calculate standard deviation. There is a moving average. There is ARIMA. Then there are machine learning and data analysis methods. STL is a machine learning method. There are some FFT-based anomaly detection methods, a lot of them again. And then there is deep learning methods, such as LSTM autoencoders and all others. So given all the hype train, let's see if deep learning methods can solve all our problems. So just to cover all the bases, there are deep learning methods typically used in anomaly detection. These are autoencoders, already mentioned in two presentations today, recurrent neural networks, GINs, CNNs, and even LLMs, which was surprising to me, to say the least. So to find out which methods are the best, we need to talk. We need to take all these popular deep learning algorithms and test them on various data sets that demonstrate all kinds of anomalies, but This is a huge undertaking, and it probably worth a couple of PhD theses. So fortunately, we came across some research papers asking the very same questions. And findings are quite interesting. These findings shed some light on whether deep learning is a silver bullet for anomaly detection or not. So let's see what research says. One study with a bold title, Current Time Series Anomaly Detection Benchmarks are Flawed, states that most anomaly detection algorithms, especially ones based on deep learning, have 10 or more parameters. The same article also points out that we are not aware of single papers that presents forceful and reproducible evidence that deep learning performs much simpler methods. The same research illustrates this point with an example. In the top graph, we see the original data with Telemanum algorithm. This shows in lines in red, in blue, show anomaly scores. And on the top graph, both are performing reasonably well on this data set. But in the bottom graph, after adding some noise to the data, things change. We see that this Telemanum algorithm, which I think probably based on LSTM, struggles, but Discord algorithm, which we will learn about later on, still handles this data pretty well. There is a great study called Anomaly Detection in Time Series Comprehensive Evaluation by German scientists, and they evaluated more than 150 anomaly detection algorithms and made some very interesting findings. We found that deep learning approaches are not yet competitive despite the higher processing effort on training data. And another study by another German university shows that classical machine learning methods often outperform deep learning methods. And another research shares the similar opinion. Those deploying methods, even though potentially useful, do not bring much additional value for the task of anomaly detection, and their complexity not justified. Even more worrisome that they managed to create, up to now, an illusion of progress. So, yeah, we have some opinions on deep learning. We have some researches. We have some pretty comprehensive test data, and we find that not everything matches these requirements. So performance and efficiency, these models are resource intensive, and this is probably one everybody agrees with. Ease of use, they often require tuning a large number of parameters, not to mention most of them are supervised or semi-supervised. Easy to understand and interpret results, not really. Deep learning can be a bit of black box, making it pretty hard to explain these results. That said, no research argued that these models couldn't work for subsequent based anomalies or anomalies with multiple seasonalities. So while deep learning shouldn't be discounted, it doesn't seem like an all-rounder for Zabbix. So the next question is, what is the best approach for Zabbix? The research already mentioned anomaly detection in time series, a comprehensive evaluation lists top anomaly detection algorithms in many of them are distance-based, marked by the green dots in the picture. Distance-based algorithms detect anomalies by measuring distance between subsequences, assuming that normal subsequences cluster together while anomalies stand out by being more distant. These algorithms are great at detecting especially subsequent-based anomalies. But when it comes to simplicity, performance, and number of parameters to tune, there is one class of algorithms which stands out about the rest, and this is matrix profile. Even though it's a new concept, the general idea stems from distance matrices known for decades. But distance matrices have been very hard to use for any serious data analysis because of big computing power and very unfriendly memory requirements. So in 2016, researchers from University of California came with this brilliant idea to condense the matrix into vector and provided an algorithm to do it much faster. And they also provided a framework to interpret the data. So matrix profile is not an algorithm. There are many algorithms behind this method, and there are variations, but they all do the very same things and calculate so-called matrix profile vector. It works by calculating nearest neighbors to detect problems. It works with subsequences of constant length and helps to identify motifs which are similar subsequences. It is their terminology, and discords which are anomalies. It is fast on long subsequences, and it has predictable time complexity, meaning that you can trust it to scale well with large time series. Matrix profile has several strengths that make it stand out. First is applicable for both subsequence and point-based anomalies, which gives it a lot of flexibility. It's also easily parallel, which gives a good scalability. Another advantage is that there is no false positives. You can't beat math, and if something flagged, you can trust it. It requires no tuning parameters at all, apart from subsequence length. And it is already being used in many different domains. So it's a versatile method that's proven to be useful in wide range of real-world applications. So how is it calculated? For the sake of simplicity, let's consider this very small graph. This is a brute force method that is rarely used in practice, but gives a good understanding about how this works. So even though it may look a little bit cluttered, but idea is very simple. We start by calculating distances between all subsequences, creating a distance matrix. And then for each subsequence, we find the minimum distance in every row. We take the minimum value from every row and put them into one single vector and compose profile. So finally, we take those minimums and maximums, and minimums in the matrix profile will mean similar subsequences, whereas maximum value will mean anomaly, because the maximum value will just show subsequence which is not like any other subsequence on our time series. Let's look at some examples. This data came from Numenta Anomaly benchmark. It simulates system load, and we see that there is no clear seasonality. There are many zeros, there are some random spikes, and we can intuitively spot anomaly. Here, around 11th of April, where the spikes became more frequent. But applying methods like STL or Z-scores would result in many false positives in this case. So this is just, for example, how STL analysis looks. Not good at all, because there is a lot of outliers in residual component. Now let's take a look at matrix profile for this time series. In the top graph, you see matrix profile calculated, and the highest value points at discord. And in the bottom graph, we can see the actual subsequence anomaly that corresponds to the highest value. Another one is CPU utilization. This is a real time series of CPU utilization for EC2 instance, and it seems like value is around 100%. It is a normal state, but something happened and utilization dropped. There is a clear anomaly. If we calculate matrix profile, we find that these algorithms didn't find what we expected it to find. It found something different, and this is because that by default matrix profile uses normalization. So by default, these algorithms finds only similar or different subsequences, regardless of what are absolute values of this data. But if we turn normalization off, this is what we see. Matrix profile clearly shows the only anomaly in this time series. Another example is ECG. So we see here that there is so-called wandering baseline, which can confuse many anomaly detection algorithms, and there is just one tiny and not very unnoticeable drop. But if we calculate profile for this example, we get this one only discord. So let's see how this matrix profile stacks against Zabbix requirements. Performance and efficiency, yes. Easy to use. There virtually no any tuning required. It's easy to understand and interpret results, and of course subsequence-based anomalies covered. The only thing which is missing is multiple seasonalities. That's why I'm also considering other algorithms. So just very quick overview of a couple of them, just to show the direction of our research. One thing we consider is a profit algorithm released by Facebook in 2017. It supports unlimited seasonalities and is easy to use, but it designed for business data and with the primary goal is forecasting. And another one is MSTL. It's a new development in this area, and what is good that it doesn't invent anything like drastically new. It just iterates on STL, but nevertheless, it supports multiple seasonalities and it detects them automatically. It has some tuning parameters, yes, but it is faster than Profit. So, coming to Zabbix, trigger functions, trend-MP, which will use matrix profile analysis to return the number of anomalies. Then we are going to implement trend-M-season for multi-seasonal time series, and it should have simpler interface, but work similarly to trend-STL. We are also exploring the idea of a super function that combines multiple anomaly detection methods in one call. And even though there is no guarantee on the specific names or interfaces yet, one thing is for sure, that better anomaly detection tools are coming to Zabbix soon. So, just a quick note about our further plans and research. We are going to, at some point, include anomaly detection in standard templates. We will be looking into other algorithms, Merlin and Walmot. Both are built on matrix profile, but both exercise idea of varying subsequences, which means for us, this means that if we will use them, we can get rid even of subsequence lens selection. Multivariate anomaly detection. We would like to untie these anomaly detection functions from trends, and we would also love to mark anomalies on graphs. So basically, this is it. There are some references if you want to deep dive into these topics. There are some very interesting researches and articles. So that's it from me about this. Thank you.